for helping the needy.
Right, see,
I don't understand the concept, but then I'm not a big shot.
her motives were pure. All she wanted to do was give the money to help the needy. She did not want to benefit from the needy's plight.
Yeah. Well, that's why I wanted her to call in. Now that you're speaking for her.
She is so vain that she doesn't have to listen.
You understand when everybody when you big tire somebody see how big they are?
No.
What am I going to do? 5 minutes flat? Supposed to hide down behind it? Can't read it. Has this got sound too? Yes, real good. You take a picture of me for there's a tire.
But you're doing the work.
Now, this is really difficult. All there is, folks. Your turn, Henry. Get on the forklift and drive around.
checked that car better than any I've ever checked. what a maintenance man does.
Well, that ain't a whole lot.
he been doing? Working with that? Look at Roger. No. Nobody recognized you anyway. You don't have your glasses on. What, Mary, no sport? No sport.
Nighthawk 1, direct to the airport is approved. Remain south of 27 left. I've got one departure. So too, Nighthawk 1 is a Beach 99 just off of 27 left. He's on a runway heading at 4,000. Let me know when you have him in sight, please. On our front, we're going to safe now. Roger, Nighthawk 1. You can plan on going direct to the airport. Behind him, just hold short of 14 right. Okay. Roger, maintain visual with him. Continue inbound towards the airport. Hold short of 14 right for landing traffic. 20 in New York, for the landing. Hold right, 18011. Restrict 4S11 on a mile. Yeah, final. Yeah, that's it.
Probably nothing in this world leads a harder life than an aircraft tire. Its whole existence is pure punishment. Enormous loads, stinging cold, and blistering heat. Damaging bruises and deep cuts. Cruel scrapes and contaminating spills. Severe torture from the worst kinds of weather. Plus all the harmful effects of too much pressure. Or even worse, the lack of it. All these things can be death on tires. So it's up to all of us to make them last as long as possible, to extend their service life to the practical limit. We at B.F. Goodrich have the first responsibility to build in as much quality and reliability as is humanly possible, as we have from Lindbergh's time to today's space shuttle. And then it's your job to maintain that quality through vigilant and thorough inspections. The care and maintenance of aircraft tires should be considered as a complete and constant series of checkpoints. Checkpoints for safety. Checkpoints for performance. Checkpoints for economy. But before we take off on a discussion of these checkpoints, we need a good understanding of the construction of an aircraft tire. We need to look at the inside story, the elements that make up a tire, and the tough demands that they must meet. Here's a cross-section of a typical tire, the kind you deal with every day. First, there are the beads. These carefully bundled steel wires are actually the foundation of the tire. Embedded in rubber, they will anchor the plies and permit the tire to be mounted firmly to the wheel. Then, the inner liner. It contains special rubber to resist air diffusion and maintain proper pressure. The carcass is painstakingly assembled with multiple layers of rubber-coated nylon. These plies are placed in an exacting configuration for high-speed stability. Each ply is wrapped around the beads for strength and integrity. Chafer strips are applied to protect the beads during tire mounting and demounting. The undertread is added to bond the carcass to the tread and to permit retreading. Now the tread rubber is applied. It is a special compound designed for toughness and durability in the difficult environment it will soon face. Finally, the sidewall rubber is eased into alignment. And the whole green tire is cured in a giant press. Here, at temperatures up to 388 degrees and pressures reaching 400 pounds per square inch, the aircraft tire takes on its familiar shape. A serial number is added during this process so that the history of each individual tire can be traced. The tire is inspected. Vents are added to the sidewall to allow diffused gases to escape. The tire is balanced and marked with a red dot for alignment with the valve stem on the aircraft wheel. Quality is built into each tire. All along the line, the tire is weighed and inspected for any possible flaws. The seasoned tire builder puts his name in each tire he builds. His promise to you that he has built it carefully, accurately, and to exacting specifications. Before a tire design ever reaches full production, BFG carefully evaluates it with a battery of test procedures, including in-service monitoring. Rigorous static load testing verifies strength and sizing. Evaluation by multi-stage dynamometers that can simulate speeds in excess of 300 miles an hour and loadings over 100,000 pounds assures that the tire will perform as it should under a variety of takeoff and landing conditions. So when our new aircraft tires are shipped to you, you can be confident that they are as strong and as safe as we can make them. You'll find this same rigorous quality approach at work at our retreading facilities, too. Retreading is a critical part of extending the service life of an aircraft tire. Why? Because a new tire can cost from $500 to $1,500, while a retread costs only $75 to $300. Depending on individual airline operations, you can get as many as 10 retreads per tire carcass. Although the retreading process is less complicated, it still requires the utmost care. First, the tire undergoes visual and air needle inspection to identify potential problems. Then, all tread remnants, the undertread, the reinforcing plies, and remaining gum are meticulously stripped away. An Orbitread machine applies a set thickness of tread rubber around the circumference, and the tire is balanced and inspected. In addition to a serial number, further identifying information is embossed into the tire to facilitate tracing its history. Then it is put into a mold, heated under great pressure, trimmed, and inspected again. Depending upon airline requirements, retreads can be subjected to careful examination by holographic equipment. Lasers search for internal conditions which could affect the service life of the tire. An airline can spend millions of dollars for tires every year. That's an enormous investment in the tires you service. How well you protect that investment and protect the safety of the passengers who ride on the tires depends on how closely and faithfully you adhere to your tire care checkpoints. And the checkpoint that should be of primary concern is the maintenance of proper inflation pressure. Improper inflation, particularly underinflation, is a major reason for tire failure and a real danger to aircraft and passengers. It can cause excessive tread wear in the tire shoulder area or heat and flexing, which lead to ply separation and carcass degradation, all resulting in lowered tire life. It can allow the sidewalls to be crushed by the rim flanges of the wheel during landing. Or the lower sidewall and bead areas can be damaged, causing a bruise, break, or rupture of the cord body. Underinflated tires can creep or slip on the wheels when braking or under stress. And this can result in bead chafing and loss of air, plus the destruction of the tire and complete wheel assembly. Although not nearly so common a problem, overinflation increases tread wear in the tire's center, leading to reduced traction and tread life and increased tire cutting. Improper inflation of either type can create dangerous vibration and shimmy in two-wheel gears. And if dual-mounted tires carry unequal pressure, the tire with the greater pressure will carry more of a load. It could be operating beyond its capacity, which could lead to over-deflection, tread separation, blowout, and an accident. Loss of pressure is your biggest enemy in the battle to maintain proper inflation. And there are a lot of causes that are part of your checkpoints. First of all, there's normal tire growth. When a new tire is inflated for the first time, the nylon cords actually stretch, causing the cord body to grow. Result? A drop in pressure after the first 8 to 12 hours. The maintenance manual tells when the tire should be reinflated to the proper pressure. The tire should then be kept at a stable ambient temperature and the pressure checked again after 12 hours. With tubeless tires, molecules of compressed gas must be able to diffuse through the sidewall vents. This is necessary to prevent ply separations, but it must also be compensated for. After tire growth is allowed for, the appearance of bubbles when a soap solution is applied to the vents will show diffusion. The pressure should then be checked. If there is a loss in excess of the manual's requirements for a 24-hour period, there may be a leak in the tire or wheel assembly. One cause of pressure loss is leaks at the valve stem or core. Your checkpoint here is to add a small amount of water to the end of the stem and look for bubbles. If they appear, release all of the pressure, replace the valve core, and check again. And always check to see if each valve has a proper valve cap and that it is screwed on firmly. The cap must be screwed on by hand, or you can run the risk of stripping the threads. Tubeless tires can leak at the valve seal, so make sure that the surrounding area has no scratches, gouges, or foreign materials. An obvious source of pressure loss is tire injury, from cuts, punctures, and other foreign object damage. The checkpoint here is to look for embedded objects, and be sure that you look when the tire is inflated. Mark the damaged area and deflate the tire. If you remove an object, do it with a blunt awl or medium-sized screwdriver. Pry out the object, but be careful not to enlarge the injury or drive it into the cord body. It's very important to deflate the tire completely before you attempt to remove an object. If the object is obstructing a hole or a similar point of air loss, it could become self-propelled during removal attempts, causing serious personal injury. If the tire damage has exposed or penetrated the cord body, check your maintenance manual for cut limits before you remove the tire. Depending on its condition, the tire can possibly be retreaded or repaired. O-rings can be an all-around cause of pressure loss with tubeless tires. Twisting during installation, failure to lubricate properly, the wrong size or type of O-ring, or an O-ring of the wrong compound can all spell air leakage. If you reuse O-rings, make sure they're not deformed, damaged, or deteriorated in any way. Often, a faulty thermal fuse plug will cause leakage. You've got to keep the sealing surface clean and scratch-free. Lubricate the plug before installation, and use properly specified seals that have no damage or distortion. Damaged or improperly seated beads can also cause pressure loss. Be sure to check the bead area for any problems. And then there's a whole list of wheel conditions that must be included in your checkpoints for pressure loss. You must have properly torqued tie bolts. Make certain you use adequate lubrication and the proper torquing method to get the right O-ring compression for all temperature conditions. The improper use of tire irons or bead breakers will show up as wheel scratches and gouges, with resultant leakage of the O-ring seal or bead-to-wheel contact area. Leakage can also occur at the bead-to-wheel area from corrosion and wear. This is checked during wheel buildup. Always see to it that the wheel sealing surfaces have your seal of approval. Improper machining, any damage, dirt, paint, they can all cause leaks at a sealing surface. It has to be clean and smooth before you assemble a wheel. And finally, during wheel buildup, if any nut, washer, or other part falls into the tire, it is critical that you get it out. At takeoff speeds, it can slice through the inner liner and cause a blowout. Now that we've checked out the effects of improper inflation and the causes of pressure loss, let's run through our checkpoints for proper inflation procedures. As we mentioned before, you should always allow for the normal tire growth period as specified in your maintenance manual. It's quite common to have a 10% pressure loss after the first inflation. By no means put the tire in service until it has gone through the inflation-reinflation cycle. Don't take chances. After you've mounted the tire, the first inflation should be in a protected area. It's a standard airline industry practice to inflate aircraft tires with compressed nitrogen. This keeps moisture out of the tire and gives a stable and inert pressure. We recommend quality dial-type gauges for all tire inflation inspections. These can be handheld or, depending on the aircraft, actually installed in the wheel assembly. Above all, make sure they are accurate. Don't be a do-it-yourself gauge repairman. Have it recalibrated periodically by a specialist. And use the same gauge throughout all inflation procedures. Remember, too, that very cold weather can cause a gauge to read lower than the actual working pressure. And high temperatures will cause a higher pressure reading. The ideal time to check inflation pressure is when tires are cool. Wait at least 2 hours after landing and 3 hours in hot weather. If this is impractical, take a reading on all same-size tires and inflate all of them to the pressure of the highest tire. Pressures will then have to be rechecked at the next overnight stop. Be sure to check pressures every day. Also, on dual-mounted tires, either main or nose, be sure they both are operating under equal pressure within the tolerances specified in your maintenance manual. Now let's take a long, hard look at damage conditions to the tread, sidewall, bead, and carcass areas. This is critical, especially when you consider that 70 to 80% of all premature tire removal is due to cuts and other damage from foreign objects. First, let's run through the various tread conditions which you might encounter that could require tire removal and replacement. Bear in mind, however, that whatever they may be, and if they are caught in time, the tire can often be retreaded or repaired. Here's one of your key checkpoints: a cut or snag from a foreign object. Your maintenance manual will tell you if a cut is small enough not to be a problem, or if you must remove the tire. Unfortunately, too many tread injuries are caused by objects: a tool, a bolt, a chunk of concrete, metal, or glass left on the ramp. If you see an object lying there, pick it up. You can head off a lot of problems that way. Here are conditions caused by rough edges in newly cross-grooved runways, especially in hot weather. This is chevron cutting. As long as the reinforcing ply is not exposed, the tire can stay on the aircraft. However, should it turn into severe tread chunking, the tire must be replaced. At takeoff speeds, a tread rib can literally peel from a bad cut and separate from the fabric ply. Remove and replace the tire. Don't let a skid condition slide either. Identify it by the skid burn or oval-shaped flat spot caused by braking that forces wheels to lock. Check your maintenance manual for allowable skid areas because a serious skid can affect tire balance, or even worse. Here is the skid's sister, tread rubber reversion. This burn is caused by hydroplaning on a wet or icy runway. The condition requires careful inspection because, again, tire balance could be affected. This tire is suffering from groove cracking at the tread base, and it must be removed because the fabric is exposed. Here, groove cracking has extended to rib undercutting, a critical cause for removal. Hydraulic and brake fluid, jet fuel, oil, solvents, and other chemicals can cause tread deterioration. Wash the tire down with soap and water. If contamination has made the tread rubber soft and spongy, it may be cause for removal. To avoid this, keep the work area clean and cover the tires during landing gear maintenance. Of course, just plain tread wear can call for tire removal. Use a tread depth gauge to measure wear. When the tread pattern has worn to the base of the groove, or to limits specified in your maintenance manual, remove the tire for retreading. There are checkpoints for sidewall and carcass conditions too, like cuts and snags from foreign objects picked up on ramps or runways, one of the biggest causes of early tire removal. If an injury reaches the fabric, remove and replace. But again, try to prevent this problem. If you see something on the ramp that shouldn't be there, pick it up. And use care in handling tires. A standard forklift can cause a serious cut. Radial cracks that go down to the fabric also spell tire removal. Checking and cracking from weather or ozone show up in random patterns like this. The tire must be removed if you can see the fabric. Ozone cracking can occur even when a tire is not on an aircraft, so tires should be stored away from electric motors and bright lights. Here's cause for immediate tire removal: sidewall separation from the carcass. A side note for sidewalls, you'll sometimes see a small amount of rubber on the sidewall of a retread. It's caused by flashing mold overflow. The strip can simply be peeled off with no damage to the retread. And finally, an impact break from a hard landing or an object penetration can rupture the tire's carcass. Remove this tire immediately. There are 4 other conditions that can cause tire damage, even though there may be no visual injury. First is the rejected takeoff tire. It usually lands on the scrap heap because you never know what permanent damage it may have received. The second is the tire that has been run flat or partially flat. It must be removed for inspection. And then there's the flat tire's mate. Because of a possible overload, it too must be returned for a holographic analysis. And fourth is a tire suffering from brake heat damage. Bead deterioration extends from the wheel flange area to the bead toe. You can get severely blistered rubber and melted nylon fabric. You can also get a tire that may have to be scrapped. In your inspection of the conditions of aircraft tires, it is vital to have a definite schedule of procedures. So let's summarize with a checklist of checkpoints for inspection of mounted tires. Tires should be inspected for proper alignment of the red balance dot and valve stem. If the balance dot and valve stem are not aligned properly, tires can vibrate or experience excessive wear in one area. Always test for pressure loss. If there seems to be abnormal loss, check all the points where a leak could occur. Look for the whole range of tire injuries to treads and sidewalls, which you have seen here. Be sure to mark all damaged areas with a light-colored crayon, wax marker, or paint stick, and mark them immediately. Otherwise, when the tire is deflated, the inspector may not be able to find them again. Inspect treads for wear with your depth gauge, and remove tires at the right time for retreading. Also check for wheel damage, and make certain that the tires are of the proper size and ply rating. And finally, make sure you have no blown fuse plugs. If you find one, remove the tire and mark it for special inspection. These are your tire checkpoints. Don't neglect to perform them. Checkpoints can make a difference, a big one. It allows us to focus together on avoiding tire damage and prolonging tire life. Properly followed, checkpoints can help you spot costly trouble long before it happens. Checkpoints, a key to fewer delays, fewer emergencies. It adds an extra measure of service precision to deliver all the safety, performance, and quality built in to B.F. Goodrich aircraft tires. Checkpoints, working together with you.